PostgreSQL is a powerful open-source object relational database system that uses and extends the SQL language combined with many features that safely store and scale the most complicated data workloads. The origins of PostgreSQL date back to 1986 as part of the Postgres project at the University of California at Berkeley, and has more than 35 years of active development on the core platform. PostgreSQL runs on all major operating systems and has been ACID compliant since 2001. It also has powerful add-ons such as the popular PostGIS geospatial database extender. PostgreSQL has become the open-source relational database of choice for many people and organizations. PostgreSQL architecture consists of the following processes: a server process, which manages the database files, accepts connections to the database from client applications, and performs database actions on behalf of the clients. The database server program is called Postgres, and the user's client or front-end application that performs database operations. A client could be a text-oriented tool, a graphical application, a web server that accesses the database to display web pages, or a specialized database maintenance tool. Some client applications are supplied with PostgreSQL distribution, but most are developed by users. To install PostgreSQL, we will first go to postgresql.org. Then we'll click on the download button. And since we will be installing this on a Windows machine, we will select Windows. Then select Download the installer. Then download the latest version for Windows x86-64. Once the download has completed, run the installation. Click on Next. Use the default installation directory and click on Next. PostgreSQL Server option installs the PostgreSQL database server. pgAdmin 4 option installs the PostgreSQL database GUI management tool. Stack Builder provides a GUI that allows you to download and install drivers that work with PostgreSQL. We will use Stack Builder in more advanced tutorials, so we will uncheck this option. Command Line Tools option allows you to install command line tools such as psql, pg_restore, and so on. These tools allow you to interact with the PostgreSQL database server using the command line interface. Then click on Next. For data directory, we will use the default setting and click Next. Next, we will need to create the super user password that will be used by PostgreSQL. So we will enter the password and then re-enter it a second time. Then click on Next. Next, we will select the port number the server should listen on. We need to ensure that port 5432 is not in use. To do this, we need to run the resource monitor. Note that you do need to be an administrator to run this. To run the resource monitor, you press the Windows key plus the R key. Then enter resmon.exe, then OK. Select Network tab, then Listening Ports. Then verify that port 5432 is not in use. If it is, then enter a port number that is not in use, but in our case we can see that 5432 is not in use. Then click on Next. For advanced options, we will accept the default for the local database cluster, then click on Next. View the pre-installation summary. If there is anything that does not look correct, click on the back button to go back and make any corrections. Then click on Next. Then click on Next to begin the installation. Then click on Finish to complete the installation. psql, which is an SQL shell, is a terminal-based program where you can write and execute SQL syntax using the command line terminal. It enables users to execute queries efficiently and manage databases effectively. In this next video, you will learn how to do the following using psql. Launch psql command line terminal, list all available databases, create a database, create a table and its columns, insert data, and show data using a select statement. To launch the psql command line tool, click on the Start button and select SQL Shell. Then select the default of localhost for server, select the default of Postgres for database, select the default of 5432 for port, and select the default of Postgres for username. For the password, enter the same superuser password that was entered during the installation of PostgreSQL. Entering help shows a list of commands that can be used for different help topics. Entering \l shows a list of databases in this cluster. Next, we will create a database named My Company. Here we can see the database that we just created. Next, we will connect to My Company database. Then we will create a table named Employee with 5 columns, the first column being a serial primary key named ID. Entering a \d shows a list of the tables for this database. Here we can see the employee table that was just added. Entering a \d with the table name shows the properties of the employee table. Next, we will insert data into the employee table using the Insert Into statement. Then we will show the data from the employee table using the Select statement. Here we can see the data that we just added. Next, we will create a salary table with an ID column as a primary key, and an employee ID column that is a foreign key, which references the ID column of the employee table. \d shows the salary table we just entered, and \d with the table name shows the properties of the salary table. Then we will insert data into the salary table and show the data we just entered. In the previous video, we learned how to connect to the database using the SQL shell psql application, which is a command-based application that allows us to interact with the PostgreSQL database. However, sometimes you might want to work with PostgreSQL databases by using an intuitive GUI tool. pgAdmin is the most popular and feature-rich open-source administration and development platform for PostgreSQL. pgAdmin tool is a free GUI tool and may be used on Linux, Unix, Mac OS, and Windows to manage PostgreSQL and EDB Advanced Server 11 and above. In this next video, you will learn how to work with PostgreSQL using pgAdmin. To launch pgAdmin, click on the Start button, then in Search, type pgAdmin and select pgAdmin 4. In Object Explorer, click on the Servers node. Select Save Password if you don't want to enter the password each time you launch pgAdmin. Enter the superuser password that was set during the installation of PostgreSQL. Next, we will create a database. To do this, we will right-click on the Databases node and select Create Database. In the Database field, we'll enter the name of our database, My Company, then click on Save. To create a table in the My Company database, we will expand the Schemas node and right-click on Tables and select Create Table. In the Name field, we will enter the name of our table, Employee. Then select the Columns tab and select the plus sign to add a new column. In the Name field, for columns, we'll enter ID and select Serial as its data type, which creates an auto-incrementing integer column. Then select Not Null and Primary Key. Next, we will add another column named Employee Number of type integer, and a column named First Name of type text, and a column named Last Name of type text, and the column named Hire Date of type date. Then click on Save. Expanding Employee and Columns, we can see the columns that were just entered. Next, we will add data to the Employee table. Right-click on the Employee table and select View Edit Data All Rows. To add data, we will click on the Add Row button. Since the data type for ID column is Serial, which auto-increments, we will not enter any data for this column. Next, we will enter data for Employee Number, First Name, Last Name, and Hire Date. Then select Save Data Changes to insert this row into the Employee table. Note that a value of 1 was automatically entered for the ID column. In this next example, we will enter data using the Insert Into statement. To do this, we will open a Query Tool window and add data to the Employee table using an Insert Into statement. Then we will click on Execute Script to add the data. Next, we will use a Select statement to show the data of the Employee table. Next, we will create a Salary table. Then add an ID column of type Serial that's not null and a primary key. Next, we will add a foreign key column named Employee ID of type integer that references the ID column of the Employee table. To make this a foreign key column, we will click on the Constraints tab, then the Foreign Key tab, and select Plus to add a constraint for this column. Next, select the Columns tab. In Local Column, select the Employee ID column of the Salary table. In References, select the Employee table, and in Referencing, select the ID column. Next, we will add the name of this constraint as salary underscore employee ID underscore F key, which is a common naming convention for a foreign key constraint, which is typically table name underscore foreign key column underscore F key. Then click on the Add button. Next, we will add a salary column of type money and a salary start date of type date. Then click on Save. Selecting Constraints, we can see the constraint was just added. Next, we will add data to the salary table using two Insert Into statements, and then show the data that was just added. PostgreSQL provides the standard SQL Boolean type. The Boolean data type can have the states true, false, and a third state unknown, which is represented by the SQL null value. SQL defines these character types for storing strings: a variable length limit, a fixed length, and a variable unlimited length. Monetary type stores a currency amount with a fixed fractional precision. Floating point numbers is not recommended to handle money due to the potential for rounding errors. BYTEA is a binary data type that you can use to store binary strings or byte sequences. BYTEA stands for binary array. The maximum size of a BYTEA column is 1 gigabyte. It means you can only store binary data up to 1 gigabyte in a single BYTEA column. For this example, we will launch a PowerShell window and run it as an administrator. Then we will go to the bin directory where PostgreSQL has been installed. Then we will launch psql from the bin directory. First, we will create a database named MyBinaryData. Then we will connect to the database. Next, we will create a table named BinaryData with a column named Data of type BYTEA. Next, we will insert some binary data using a hexadecimal format. Then we will select the data itself. Next, we will look at an example of inserting data from an image file. First, we will create a table named Image with a column named Data of type BYTEA. Then we will insert data into the BYTEA column from a JPEG file using the function pg_read_binary_file. Next, we will view the data using a select statement. Note the use of the encode function to display the contents. Large objects, also known as blobs or binary long objects, are used to hold data in the database that cannot be stored in a normal SQL table. They are stored in a separate table in a special format and are referenced from your own tables by an OID value. Streaming access is useful when working with data values that are too large to manipulate conventionally as a whole. A large object cannot exceed 4 terabytes for Postgres version 9.3 or newer, or 2 gigabytes for older versions. To work with blobs in PostgreSQL, you'll need to use specific functions provided by PostgreSQL. The basic operations include creating a large object, opening it, reading from it, writing to it, seeking within it, and finally closing it. Some of the large object functions that are available are lo_create. This creates a new large object and returns the OID of the newly created object. lo_open takes 2 parameters. The first is the OID of the large object to open, and the second is a mode parameter, which is either inv_read or inv_write. lo_write takes 2 parameters. The first is the OID of the large object to write to, and the second is the actual data to insert. lo_read takes 2 parameters. The first is the OID of the large object to read from, and the second is the number of bytes to read. lo_lseek moves the current location pointer for the large object descriptor identified by its OID to the new location specified by offset. Valid values for whence are seek_set, which is seek from object start, seek_cur, which is seek from current position, and seek_end, which is seek from the object end. lo_close closes the large object. lo_unlink deletes the large object. lo_import imports a file from the file system as a large object and returns the OID of the newly created large object. lo_export exports the large object to the file specified. In this example of using large objects, we will use the pgAdmin tool. First, we will create a function in the MyBinary database. To do this, we will open a Query Tool window. Next, we will create a function named WriteLargeObject using pgSQL, which is a block-structured language that takes a parameter named bytes of type BYTEA that returns a data type of OID. Then we will call lo_create that will create an IOD. Then we will call lo_open with the OID that was created and open it for writing. Then call lo_write to write the bytes that were passed into this function. Next, we will call lo_close to close the large object and return the OID that was created. Then we will execute this script to insert this function. We can see this function was added by selecting Refresh under Functions. Next, we will open another Query Tool window and create a function for reading bytes from a large object named readLargeObject that takes two parameters, OID to read of type OID and size to read of type integer. This function returns a BYTEA data type. First, we will call lo_open with the OID of the large object to open and to open this file for reading. Then we will call lo_read with the number of bytes to read. Next, we will call lo_close and then return the bytes that were read. Finally, we will execute this script to insert this function. Next, we'll open another Query Tool window and create a table named Large Binary Data that has two columns named Name of type varchar and Large Object Ref of type OID. Next, we will write data to a large object using the function WriteLargeObject that we just created. Then we will insert into the Large Binary Data table myLargeObject and the OID that was returned from calling the WriteLargeObject function. Now we will execute the insert into statement. Next, we will select data from the Large Binary Data table. Here we can see the name and the OID that was just inserted. Now we will retrieve data from a large object using the function readLargeObject that we just created. Note the inner select statement will retrieve the OID, which will be used to pass into the readLargeObject function and pass the number of bytes to be read, which will be 4. Then we will execute the select statement. Here we can see the data retrieve matches the data that was inputted. Next, we will create a function to import the contents from a file to a large object. The function importLargeObject takes one parameter named filename of type varchar, which is the fully qualified path name of the file to import. The function returns the data type OID. The file name to import is then passed into lo_import. The function then returns the OID that was created from lo_import. Next, we will create a function that exports the contents of a large object to a file. The function exportLargeObject takes two parameters, an OID of the large object to export, and the fully qualified path name of the file to export the contents to. The function will return a data type of type integer. The function then calls lo_export with the given parameters and returns any error code from lo_export. In this example, we will import the contents of a file into our large object using the function importLargeObject that we just created. Here we will insert into the Large Binary Data table the name myJPEG file and the OID that will be returned from calling importLargeObject. We also include the fully qualified path name to be imported. Then we will execute the insert into statement. Next, we will select the data from the large binary data table. Here we can see the name and the UUID that was created after calling the above insert into statement. Next, we will export the contents of the large object into a file using the function export large object that we just created. Here, the inner select statement will retrieve the large object ref, or OID, which will then be used to pass into the export large object function and include the fully qualified path of the file to export the contents to. Here we can see the file that was exported. Next, we will use a select statement to show all of the OIDs for this database. Finally, we will show how to delete all existing large objects for this database using lo_unlink. Here we can see that all of the OIDs have been removed from this database. PostgreSQL numeric data types consist of integer data types are small int, integer, and big int. Floating point data types are decimal and numeric, which are equivalent, real, and double precision. Auto-incrementing integer data types are small serial, serial, and big serial. Date-time data types are date only, both date and time, without a time zone and with a time zone. Note you can also use the data type timestamp TZ to denote timestamp with a time zone. When you insert a value into a timestamp TZ column, PostgreSQL converts the timestamp TZ value into a UTC value and then stores the UTC value in the table. When you retrieve data from a timestamp TZ column, PostgreSQL converts the UTC value back to the time value of the time zone set by the database server, the user, or the current database connection. Time of day only, without a time zone and with a time zone, and time interval. In this example of date-time data types, we will create a database named date-time data types. Then we'll open a query tool window. Next, we'll create a table named employee that contains a column named birth date of type date. Then we'll add some data to the employee table. Note the date-time format is in the form of year, month, and day. Next, we will use a select statement to show rows whose birthdays are less than January 1st of 1856. Now we will create a table named event with a column named event start of type timestamp with no time zone, and a second column named event start TZ, which is of type timestamp TZ that has a time zone. Then we'll add data to the event table. Note the format of the timestamp, which is year, month, day, hour, minutes, and seconds. Next, we will view the data we just entered. Note how the column event start TZ shows a -5, which is the time zone for America, New York. Now we will create a table named shift with a column named start at of type time and a second column named end at of type time. Then we'll add data to the shift table. Note the format of timestamp, which is hours, minutes, and seconds. Next, we'll view the data we just entered. Next, we'll take a look at the interval data type. Here we can see in the first column how the direction parameter ago negates time as -2 months. Now we'll use subtraction of time using the interval data type. Here we can see the second column shows 1 year, 3 hours, and 20 minutes were subtracted from now. Next, using the employee table we created earlier, we'll use the age function to show the age of each row in the employee table. Here the age subtracts birth date from the current date and returns an interval as a result. Now we'll create a table named event duration that contains a column named duration that uses the interval data type. Then we'll insert some values and then show the contents of the event duration table. Here we can see the interval for the event name conference call and the interval for the event name partial workweek. PostgreSQL supports 4 output formats for interval: Postgres, which is the default, Postgres verbose, ISO 8601, and SQL standard. First, let's show what the current interval style is set to, which happens to be Postgres. Next, we'll look at an example using SQL standard. Then we'll look at an example using Postgres. Then an example using Postgres verbose. And an example using ISO 8601. This format starts with a P, followed by years, months, days, then a T, followed by hours, minutes, and seconds. Enumerated or enum data types are data types that comprise a static, ordered set of values. They are equivalent to the enum types supported in a number of programming languages. Unlike other types, enumerated types need to be created using the createType command. This type is used to store a static, ordered set of values. The syntax for createType is shown here. An example of using createType for enum is shown below. Enumerated, once created, can be used like any other types. In this example of enums, we will use pgAdmin to create an enum data type. First, we will open a query tool window in the datetime data types database. Then we will create an enum data type named workweek with the values Monday, Tuesday, Wednesday, Thursday, and Friday. Then right-clicking on the types node and selecting a refresh, we can see the enum that was just added. Then create a table named Employee Week Schedule and add a column named Day of Week of type Work Week, which is the enum that we just created. Then we will insert some data into the Employee Week Schedule table for name, day of week, and hours worked. Next, we will use a select statement to view the data that we just inserted. Geometric data types represent two-dimensional spatial objects. The most fundamental type, the point, forms the basis for all of the other types. Other geometric types are infinite line, line segment, rectangular box, geometric path on a plane, a polygon or closed geometric path on a plane, and a circle. For this example of geometric data types, we will use pgAdmin. First, we will create a database named Geometric Data Types. Then we will open a Query Tool window. Next, we will create a table named DataPoint that has a column named DataPoint of type point. Then add a data point to this table. Note that point is the building block for geometric data types. Then view the data we just entered. Next, we will create a table named Line Data that has a column named Line Data Points of type line. Then insert data into the line data table that represents an infinite line with no defined length. Here the output is in the standard form of a line, which is ax plus by plus c equals 0. Next, we will create a table named Line Segment that has a column named Line Segment Points of type LSEG. Then insert line segment data, which represents a line segment with a clear starting and ending point, and then view the data we just entered. Next, we will create a table named Box Data that has a column named Box Data Points of type box. Then insert box data, which is represented by pairs of points that are opposite corners of the box. And then view the data we just entered. Next, we will create a table named Circle Data that has a column named Circle Data Points of type circle. And then insert circle data, which is represented by a center point and a radius. Then view the data we just entered. Next, we will create a table named Path Data that has a column named Path Data Points of type path. Then insert path data, which is represented by lists of connected points. And then view the data we just entered. Next, we will create a table named Polygon Data that has a column named Polygon Data Points of type polygon. Then insert polygon data, which is represented by lists of points, which are the vertexes of the polygon. And then view the data that we just entered. Native geometry data types are the standard geometric data types provided by a database system itself, which may be more limited in spatial functionality. PostGIS provides a rich set of spatial functions and data types built on top of a database's native geometry capabilities, making it ideal for geospatial applications. The geometry data type in PostGIS would also store X and Y coordinates, but additionally allows you to perform complex spatial operations like finding the distance between 2 points and checking if a point lies within a polygon. Here are some examples of spatial functions that are available for line strings and spatial functions that are available for polygons. To use PostGIS, first we will need to install it. To do this, we will go into the bin directory of the version of PostgreSQL that was installed. Then run stackbuilder.exe and choose the port to install it on. Then click on Next. Next, open Spatial Extensions and select PostGIS 3.5 bundle for PostgreSQL 17. Then click on Next. Use the default for download directory and click on Next. You may need to wait for the downloading window to appear. Once the downloading window has completed, click on Next. Click on Agree to the license agreement and use the default selections for Choose Components and click on Next. Accept the default destination folder and click on Next. Then click on Close and then Finish. Using pgAdmin, we will create a database named Geometry. Next, we will open a query tool window. In order to use PostGIS, we will need to add the PostGIS extension to this database using the Create Extension statement. Here we can see the PostGIS extension has been added. Next, we will create a table named Geometry Data and a column named Geom of type Geometry. The Geometry data type accepts different types of geometric data, such as point, line string, and polygon. Now we will insert some geometric data. The function st_geom from text will take well-known text and convert it to a geometry data type. Using a select statement shows the actual data in blob format. Using the function st_geometry type will show the type of geometric data for each row. The function st_as_text converts the geometric data type to well-known text, also known as WKT. The function st_length shows the length of the line string. The function st_startPoint shows the first coordinate of the line string as a point. The function st_endpoint shows the last coordinate of the line string as a point. And the function st_endpoints returns the number of coordinates in the polygon. PostgreSQL offers data types to store IPv4, IPv6, and MAC addresses. It is better to use these types instead of plain text types to store network addresses, because these types offer input error checking and specialized operators and functions. The data types that are available are CIDR, INET, MAC address, and MAC address 8. Using pgAdmin, we will create a database named Network Address Data Types. Then we will open a query tool window and create a table named network_address. Next, we will create a column named IP_CIDR, which is of type CIDR, which is for IPv4 and IPv6 networks. Then we'll create a second column named IP_INET, which is of type INET, which is for IPv4 and IPv6 hosts, and networks. And a third column named Mac_Mac ADDR, which is of type Mac ADDR, which is for media access control addresses. Next, we will insert a row of data. Here we can see subnet/32 was added to the CIDR data type by default, meaning that it is a single host. We were able to add a /24 subnet to the INET data type, which is not allowed in the previous column. MAC address has a single format, which is comprised of pairs of hex digits optionally separated consistently by a colon, hyphen, or dot. Next, we will insert more rows of data. Then we will use the function family that extracts family of address on the IP_CIDR column. A value of 4 is for IPv4, and a value of 6 is for IPv6. Next, we will use the functions network and host on the IP_net column. Network returns the network part of the address, zeroing out whatever is to the right of the net mask. Host returns the IP address as text, ignoring the net mask. Then we will show an example using the between statement on the IP_CIDR column. The result of between is the range of the two addresses. Next, we will use the greater than equal operator on the IP_net column, which is used for does subnet contain or equal a subnet. Bit strings are strings of ones and zeros. They can be used to store or visualize bit masks. There are two SQL bit types, bit and bit varying, where n is a positive integer. There are also bit string operators, concatenation, and, or, exclusive or, not, shift left, and shift right. There are also bit string functions, bit count, bit length, octet length, overlay, position, substring, getBit, and setBit. Using pgAdmin, we'll create a database named the bitstring data types. Then we'll open a query tool window. Next, we will create a table named the bit data type and a column named bit_column of type bit with a fixed length of 8. Then we will insert some data. Note that bit strings are bound by single quotes, but they must be preceded by a leading B character, which may be uppercase or lowercase. This character identifies to PostgreSQL that the forthcoming constant is a bit string and not a normal string of character data. Next, we will use a select statement with a where clause. Next, we will create a table named bit varying data type. Then we'll create a column named bit_varying column of type bit varying with a variable length of 16. Then insert some data and select data using a where clause. Bit columns are often used for storing flags or Boolean values compactly. In this example, we will show you how to use a bitwise operator. We will create a table named bitFlags with a column named bitFlag of type bit with a fixed length of 8. Then we will insert 2 rows of data and use the bitwise AND operator with a where clause that will retrieve rows that have the rightmost bit set. Next, we will look at some examples using bitwise operators. First, we will use the bitwise operator for concatenation. Here we can see a 011 was appended to the bit string. Then use the bitwise AND operator. Next, use the bitwise OR operator. Then use the bitwise exclusive OR operator. Next, use the bitwise NOT operator. Now use the bitwise shift left operator. And use the bitwise shift right operator. Next, we will look at some examples using bitstring functions. First, we will use the function bit_count, which returns the number of bits set in a bit string. Then use bit_length that returns the number of bits in a bit string. And octet_length that returns the number of bytes in a bit string. Then overlay, which replaces the substring that starts at the second bit and extends for a count of 3 bits with the new substring. The position function returns the first starting index of the specified substring within the bits that are specified. In this example, the substring function extracts the substring of bits starting at the 3rd bit and stopping after 2 bits. Here the get_bit function extracts the 6th bit from the bit string. Note that the first leftmost bit is bit 0. In this example, set_bit function sets the 6th bit in the bit string to 0. Note that the first leftmost bit is bit 0. A UUID, or Universally Unique Identifiers, is a standard defined by the RFC 4122. It is a 128-bit quantity and is written as a sequence of lowercase hexadecimal digits in several groups separated by hyphens, starting with a group of 8 digits, followed by 3 groups of 4 digits, and followed by a group of 12 digits, for a total of 32 digits representing the 128 bits. PostgreSQL provides the following function that will generate a UUID. Using pgAdmin, we'll create a database named UUID Data Type. Then we will open the Query Tool window. Next, we'll create a table named UUID Data and a column named Unique ID of type UUID. Then we will insert some data. And then view the data. Next, we will insert data using the function gen_random_UUID. and then view the data. The XML data type can be used to store XML data. The function XML parse converts the string into an XML document. The syntax for XML parse is shown here. Document indicates that the input string is a complete XML document, starting with the XML declaration shown here. An example of XML parse is shown here. The function XPath is used to extract a value from an XML document. Using pgAdmin, we'll create a database named XML Data Lesson. Then we'll open a query tool window and create a table named XML Data with a column named XML Info of type XML. Then insert one row of data using the XML parse function. Next, we will insert multiple rows. Now we will retrieve the names of persons from the XML documents. Each row in the results set is an array of XML values representing persons' names. We will use the XPath function to select these nodes. Since each person has one name, the result array has only one element. Here we can see that an array type was returned, which is signified by the square brackets. Next, we will retrieve persons' names as text from the XML documents using the XPath function, which returns the text of the name node of the XML document. It returns an array that includes all matching values. The one subscript returns the first element of the array, and text casts the XML value to the text. Here we can see that the return type is of type text. Then we will retrieve the ages of persons, which returns the text of the age nodes as an array of text. The one subscript returns the first element of the array. Text casts the element to the text, and integer casts the text to an integer. Here we can see that the return type is of type integer. Next, we will retrieve the name, age, city, state, and country from the XML documents. And then find the person with the name Ada Lovelace. PostgreSQL provides two JSON data types, JSON and JSONB for storing JSON data. JSON data type stores plain JSON data that requires reparsing for each processing. JSONB data type stores JSON data in a binary format, which is faster to process, but slower to insert. In addition, JSONB supports indexing, which can be an advantage. The following are commonly used functions for creating JSON data and for searching JSON data. The following are commonly used functions for querying JSON data, modifying JSON data, and working with JSON arrays. The following are JSON commonly used functions for working with JSON objects, aggregating JSON data, and JSON utility functions. Here is a summary of the JSON operators that are available with PostgreSQL. Using pgAdmin, we'll create a database named JSON Data Lesson. Then we'll open a Query Tool window. And then create a table named JSON Data with a column named JSON Info of data type JSON. Then we'll insert one JSON object. Next, we'll insert multiple JSON objects. Next, we will use the JSON operator that will extract a JSON object field by a key named name. Now we will use an operator to extract the JSON object field by a key as text by a specified field. Next, we will extract the JSON object by the key country, which is embedded in the address document. Now we will use the JSON extract path text function that will extract a name from the JSON document. Then we will extract age from the JSON document. Next, extract address from the JSON document. And then extract state from the JSON document. Next, we'll create a table using the JSON-B data type. Here we'll create a table named JSON-B data with a column named JSON-B info and the data type JSON-B. Now we'll insert some JSON data And if you notice, it's inserted the same way as we did with the JSON data type. Now we will extract a JSON object field by a key the same way as we did when we were using the JSON data type. Since we are using the JSONB data type, we will need to use the JSONB extract path text function in order to extract the name from the JSON document. Next, we'll create a table named Customer that is a column called Name of type varchar of 255 character length, and another column named Phone Numbers of type JSONB. Now we will insert phone numbers as a JSON array. Note that the returning asterisk will return the inserted data. Next, we will extract the first element in the phone numbers array, which is denoted by 0. Array data type is an array of a collection of elements that have the same data type. Arrays can be one-dimensional, multi-dimensional, or even nested arrays. Every data type has its companion array type. For example, integer has an integer array type, and character has a character array type. If you define a user-defined data type, PostgreSQL also creates a corresponding array type automatically for you. Here are some common functions provided by PostgreSQL. Here is a list of operators provided by PostgreSQL. Using pgAdmin, we'll create a database named Array Data Lesson. Then open a Query Tool window. Then create a table named Contact Info with a column named Name of type varchar of 255 character length, and a column named Phone Numbers of type text as a single dimensional array. Then we'll insert some data and view the data we just inserted. Now we will select the phone numbers that start in the first position of the array. Here we can see that the results are only showing the phone numbers that are in the first array position. Now we will select data where the phone numbers in the second array position are equal to 408, 555, 5423. Next, we'll create a table named Consultant, and a column named Name of type text, and a column named Payment that is a single-dimensional integer array, and a column named Schedule that is a two-dimensional text array. Now we will insert some data. Note that when entering data for a two-dimensional array, both arrays must have matching extents. Next, we will view the data that was just inserted with a select statement. Next, we will insert some data that will cause an error. Here we can see that the error occurred because the two arrays do not have matching dimensions. Next, we will look at some examples of using array functions. Here, array_append will append a number to the end of an array. Here we can see that 11 was appended to the array. Array_cat will concatenate two arrays. Here we can see that the array 4, 5 was added to the array. Array_length will return the length of the requested array dimension, which in this case is the first dimension of the array. Here we can see that a length of 3 was returned. Array_prepend will prepend an element to the beginning of an array. Here we can see that the word say was added to the beginning of the array. Array_replace replaces each array element equal to the second argument with the third argument. Here we can see that the word 5 has been replaced with the word 3. Array_string converts each array element to its text representation, where in this example it is separated by a comma, and null entries are represented by an asterisk. Here we can see that null was replaced with an asterisk. The function onNest expands an array into a set of rows. Next, let's take a look at using array operators. This operator will test if each element appearing in the second array is equal to some element of the first array. The result is true since 31 and 11 in the second array are both present in the first array. This operator tests if the first array is contained by the second array. The result is true since 12 and 17 of the first array are present in the second array. This next operator will concatenate two arrays. Here we can see that both arrays have been concatenated. This next example will concatenate a single-dimensional array with a multidimensional array. Next, we will concatenate a single element onto the front of an array, which must be empty or a one-dimensional array. Here we can see that 31 was added to the front of the array. In this example, we will concatenate a single element onto the end of an array, which must be empty or one-dimensional. Here we can see that 27 has been added to the end of the array. As with everything that contains valuable data, PostgreSQL databases should be backed up regularly. While the procedure is essentially simple, it is important to have a clear understanding of the underlying techniques and assumptions. In PostgreSQL, there are two main types of database backups: logical backups and physical backups. Logical backups involve exporting data into a human-readable format, such as SQL statements. It is generally more flexible and portable, making it handy to reproduce a database in another architecture, for example, migrations. However, recovering from a logical backup is quite a slow process. This makes them practical only for migrating small to medium PostgreSQL production databases. The most common way to create logical backups and restore from them is by using the following command line utilities: pgdump, pgdumpall, and pgrestore. pgdump creates logical backups of a PostgreSQL database. It generates a script file or other formats that contain SQL statements needed to reconstruct the database to the state it was at the backup time. You can use pgdump to back up an entire database, individual tables, schemas, or other database objects. It is good practice to place a backup file in a server that is not the same as the one the PostgreSQL server is running. Let's take a look at the syntax for pgdump. The command line option F specifies the file path of the output file. -U specifies the username to connect to the database. -W prompts for the password to authenticate the connection. -J enables parallel backup by specifying the number of concurrent jobs. -F specifies the output format of the backup file. The available formats are P for plain text. That creates an SQL script file that is not compressed, which is the default behavior. C or custom is the directory output format, which is the most flexible output format that allows manual selection and reordering of archived items during a restore. Format is compressed by default. D for directory creates a directory with one file for each table and a large object being dumped. This format is compressed by default using gzip and also supports parallel dumps. T or tar format is compatible with a directory format. Extracting a tar format archive produces a valid directory format archive. The format does not support compression. First, let's open a command line prompt window. Then we'll go to the bin directory where PostgreSQL has been installed. In this example, we will use pgdump to back up the database dvdrental to a file named dvdrental.sql as a plain text SQL file, which is the default. Next, we will enter the required password for PostgreSQL. Here we can see, in the My Backups directory, the SQL script that was created from pgdump. Now we will add the -C command line option that will drop all of the dumped database objects prior to outputting the commands for creating them. Then we'll add the --ifexists command line option that will use the drop ifexist commands to drop database objects. This will suppress the does not exist errors that might otherwise be reported. Opening the SQL script file that was just created, we can see the ifexists commands have been added for the database objects. In this example, using the -ft command line option, we will create a tar format archive. Here we can see that the output is a tar format archive, which is suitable for input into using pg_restore. Next, using the -fd command line option, we will create a directory format archive of the DVD rental database. This will create a directory with one file for each table and large object that is being dumped. This format is compressed by default using gzip. Next, using the -fc command line option, we will back up the DVD rental database as a custom format archive. Here we can see the output file that was created. This format is also compressed by default and is suitable for input into pgRestore. pgDumpAll is a utility for writing out or dumping all PostgreSQL databases of a cluster into one script file. It does this by calling pgdump for each database in the cluster. The script file contains SQL commands that can be used as input to psql, which is a terminal-based front end to PostgreSQL, in order to restore the databases. The syntax for pgDumpAll is shown below. This command will prompt you to enter a password for each database in the PostgreSQL server. To suppress the password prompt, you can use the -w option as shown below. However, you will need to use a password file to do this. To create a PostgreSQL password file, you will need a text editor like Notepad++. Here you'll enter the connection for your PostgreSQL database in the format shown below. For a single database named My Company, the connection would look like the following. For all databases, the connection would look like the following. Note how the database name was replaced with an asterisk. Then you would save the file as pgpass.conf in your app data roaming PostgreSQL folder. Using pgDumpAll, we will create a backup of all of the databases to a file named alldatabases.sql. Then we will enter the password for each database that is to be backed up. Since entering a password for each database can be time-consuming, we will create a PostgreSQL password file that will automate this process. Using a text editor like Notepad++, we will enter the connection that will be used for all databases. First, we'll enter the host name, then the port number, then an asterisk that denotes all databases, the username, followed by the password. For this demo, the password is being shown as asterisks, but you would enter the PostgreSQL password here. Then we'll save this file in the app data roaming PostgreSQL folder. Since the PostgreSQL folder is not present, we will create it. Then we will save this file as pgpass.conf. Now we will add the -w command line option that will suppress the password prompt for each database. Here we can see that the password prompt no longer appears. Now we will add the -c command line option that drops databases during restore operation, and the --if exists command line option that ignores errors if any of the objects exist in the destination database. Using a text editor, we will look at alldatabases.sql file that was just created. We can see that all of the drop database commands have been added for every database to be restored. To restore from a plain SQL script file that was created using pgdump, we would use psql with the syntax shown below. To restore from a plain SQL script file that was created using pgdumpall, we would use psql with the syntax shown below. Note that if a database exists, restoring it will generate a database exists error unless the -c if exists command line option was used when creating the script file. If the -c if exists command line option was not used, it will be necessary to drop the database followed by creating it prior to restoring any databases. In this example, we will restore the DVD rental database using the plain SQL script file we had previously created. In a command prompt window, we will connect to PostgreSQL using the psql command line tool. Then we will enter the PostgreSQL password. Next, we will list all of the databases. Here we can see that the database DVD rental is present. Prior to restoring it, we will need to drop this database, followed by creating it. Now we will exit from the psql command line tool. Now we will restore the database using the plain SQL script file dvdrental.sql. Here we can see all of the SQL statements being executed to complete the creation of the DVD rental database. Next, we will restore the DVD rental database using the plain SQL script file that used the -c if exists command line option. Note that it will not be necessary to drop and create the DVD rental database since the script file includes if exist commands. pgrestore is used for restoring from a tar file, directory, or a custom format created using pgdump, not from a plain SQL script file. This allows for selective restoration of specific database objects, providing flexibility in the recovery process. It is compatible with other SQL-compliant database systems, enhancing its utility as a migration tool. The syntax for pgrestore is shown below. In this example, we will use pgrestore utility for restoring the DVD rental database from an archive created by pgdump in one of the non-plain text formats. First, we will need to drop the DVD rental database, followed by creating the DVD rental database. Next, we will restore the DVD rental database from a tar archive backup. In this next example, we will restore from the same tar archive backup, but we will include the command line option -C, which creates the target database before proceeding with the restoration, and -c, which drops any existing database objects before creating them, and the -- if exists. When used with the -c, will ignore errors if the database being created already exists. And the -d Postgres is used because pgrestore needs to connect to an existing database to create the new database specified in the backup file. In this next example, we will restore the DVD rental database from a directory format backup. Next, we will restore the DVD rental database from a custom directory format backup. Physical backups are mostly used for disaster recovery and data archiving. As your database grows to the size of a few gigabytes, backing it up through physical backups is more ideal than through logical backups. If you're operating a production database, you'll want to maintain up-to-date physical backups and a write-ahead log, also known as WAL, to recover your database when failure occurs. Whenever a transaction modifies the database, PostgreSQL first writes the changes to a log file before updating any data files on the disk. This log file is referred to as the WAL log. File system backups refers to the process of directly copying the directories and files that PostgreSQL uses to store its data, resulting in a complete representation of the database at a specific moment in time. Point-in-time recovery, also known as PITR, enables administrators to restore a PostgreSQL database to a specific moment in the past. Postgres also generates write-ahead log files, which can be used together with a backed-up file system to recover a database up to any chosen point in time. When disaster strikes, this is one of the best options for recreating your database up to the point right before the unfortunate happens. This greatly minimizes recovery point objective, or RPO, which is the amount of data that can be lost during a system failure measured in time. Even better, tools such as WALG, which is an open source continuous archiving tool, help simplify the steps involved in setting this up. PG-based backup is used to take a base backup of a running PostgreSQL database cluster. The backup is taken without affecting other clients of the database and can be used for point-in-time recovery. When used to take a full backup, it makes an exact copy of the database cluster's files. It is not possible to back up individual databases or database objects. For selective backups, another tool such as pgdump must be used. When used to take an incremental backup, some files that would have been part of a full backup may be replaced with incremental versions of the same files, containing only those blocks that have been modified since the reference backup. Below is the syntax of PG-based backup. This command should be run as the Postgres user. The following is a list of the command line options that are available. In this example, we will take a look on how to use pg_base backup command line. First, we'll launch a command prompt window. Then we'll go to the bin directory of where PostgreSQL was installed. Then we'll enter pg_base backup with its command line options: the host name, the port number, the username, the location where to save the backup, -ft, that indicates the tar format should be used, -z, that indicates that the tar files will be compressed, -xs, which indicates that WAL files will stream to the backup, which is the default behavior, -p, that indicates that progress information is written to the standard out during this process, and -c fast, which is the parameter that indicates that a checkpoint is taken immediately. Here we can see the backup files that were created as compressed gzip files in the full backup folder. The following are the steps for restoring from a base backup. First, stop the Postgres service. Then remove the subfolders and files in the PostgreSQL data folder. Then extract the base tar.gz file that was created using pg base backup into the PostgreSQL data folder. Then create a folder called pg_wal inside our backups folder. Then extract the pg_wal tar.gz file into the new pgwal folder that we just created. Next, create a recovery.signal file in the PostgreSQL data folder. Note that this step is for PostgreSQL versions 12 or later. The recovery.signal file is an empty file that indicates to the server that it should start up in targeted recovery mode. The recovery.signal file will be removed once the recovery target is reached, unless recovery target action is set to shut down. Now append the restore command in the PostgreSQL conf file. The restore command syntax looks like the following. The wal files archive folder is the same folder that was created in step 4. The restore command is a shell command that is automatically invoked by PostgreSQL during the recovery process whenever a required wal file is not found in the PostgreSQL data pgwal folder. It will copy wal files from an archive to the PostgreSQL data pgwal folder. Next, start the Postgres service, then remove the restore command from the PostgreSQL.conf file after the server is online. In this example of restoring from a base backup, we will use a PowerShell window. Note that you will need to run this PowerShell window as an administrator. First, we will stop the Postgres service. Then we will remove the subfolders and files in the PostgreSQL data folder. Next, we will extract the base tar.gz file that was created when using pg base backup into the PostgreSQL data folder. Here we can see a listing of all of the files that are being extracted. Next, we will create a folder called pg_wal inside our backups folder. Now we will extract the pg_wal tar.gz file into the new pg_wal folder that we just created. Next, we will create the recovery.signal file in the PostgreSQL data folder. Then we will append the restore command in the PostgreSQL.conf file. Next, we will start the Postgres service. Now we will remove the restore command from the PostgreSQL.conf file. Note that all of the commands that we have just executed can be run from a PowerShell script file shown here. Incremental backups allow you to back up only the changes made since the last backup. This can significantly reduce the time and storage required for backups, especially for large databases. Taking full backups of a large database can be lengthy and a resource-intensive process. A good workaround to mitigate this is to combine full backups with incremental backups. For example, creating full backups less frequently, like once a week, and frequently copying the data that has changed since the last full backup, like once a day. PG-based backup has important limitations. Incremental backups are not supported in PG-based backup prior to version 17. To address the constraints of PG-based backup, the PostgreSQL community built tools like pgBackrest. pgBackrest supports both full and incremental backups, but is not supported in Windows. However, incremental backups are now supported in version 17 of PG-based backup. Postgres version 17 comes with a new background worker process called WAL Summarizer Process, which creates summaries of WAL files in a directory called pg_wal/summaries. By default, this process is not turned on, but it needs to be for incremental backups to work. To turn it on, use the new configuration setting summarize_WAL equal to on. To create an incremental backup, first create a full backup. This serves as the baseline for incremental backups. The backup_manifest file generated here is essential for incremental backups. After some data changes occur, create the first incremental backup. This uses the backup_manifest file from the full backup to capture only the changes made since that backup. When more changes occur, create the second incremental backup using the backup_manifest file from the first incremental backup. This same process is used for third, fourth, and all other incremental backups. To perform an incremental backup, you will first need to take a full backup using the syntax shown here. To take your first incremental backup, you would use the syntax shown here. Note that the incremental command line option has been included. Here we reference the backup_manifest file that was created during the full backup. To take a second incremental backup, it will reference the backup_manifest file that was created in the first incremental backup. This same process is used for the third, fourth, and other incremental backups. For this example of an incremental backup, I have installed PostgreSQL version 17. First, we will launch a command prompt window. Then we will go to the bin directory where PostgreSQL has been installed. First, we will go into psql, which is the PostgreSQL interactive terminal. Then we will look at a setting for summarize_WAL. Here we can see that it is set to off. However, we need to set it to on in order to do incremental backups. To set summarize_WAL to on, we will use the alter system command. Next, we will need to reload the configuration file by using select pg_reload_conf. Note that this will reload the configuration file without the need for restarting the Postgres service. Then we will verify that the summarize_WAL has been set to on. Next, we will enter the command to create a full backup. Now we will enter a command to create our first incremental backup. Note that we are referencing the backup underscore manifest file that was created during the full backup. Now we will enter the command that will take a second incremental backup. Here we will reference the backup underscore manifest file that was created during the first incremental backup. To restore from an incremental backup requires the use of pg underscore combine backup command line utility. pg combine backup is a core utility for reconstructing a full backup from a base backup and associated incremental backups. Backups should be provided in the series of order starting with the full backup, followed by incremental backup 1, incremental backup 2, and so on. Missing an incremental backup or failing to start with a full backup will result in an error. The syntax for using pg combine backup is shown below. First, you start off with the location of the full backup, followed by the location of the first incremental backup, then the location of the second incremental backup, and so on. The -O option specifies the output folder where the backup will be restored. In this example of restoring from an incremental backup, we will use a PowerShell window. Note that you will need to run the PowerShell window as an administrator. Then we will go to the bin directory where PostgreSQL has been installed. Then we will create the Postgres restore folder structure seen here. Then we will extract the base.tar.gz file from the Postgres backups folder into the Postgres restore full backup folder. Next, we will extract the pg underscore wal.tar.gz file from the Postgres backups folder into the Postgres restore pg underscore wal folder. Then we will copy the backup underscore manifest file from the Postgres backups folder into the Postgres restore full backup folder. Then we will create the incremental backup 1 folder structure and follow the same extraction procedure for the incremental backup 1 folder that we had done previously. Next, we will do the same extraction procedure for the incremental backup 2 folder. Next, we will use the pg underscore combine backup command line utility to reconstruct a synthetic full backup from an incremental backup and the earlier backups upon which it depends. Here we will specify all of the required backups on the command line from oldest to newest. That is, the first backup directory should be the path to the full backup, and the last should be the path of the final incremental backup that you wish to restore. The reconstructed backup will be written to the output directory specified by the -O command line option. Next, we will stop the Postgres service. Then we will remove all items and subfolders within the PostgreSQL data folder. This command will not remove the data folder itself. Doing this, we will maintain the user permissions on this folder. Now we will copy the data that we restored using pg combine backup to the PostgreSQL data folder. Next, we will restart the Postgres service and this will complete our restore operation. All of the commands that we have just executed can also be run using a PowerShell script shown here. PostgreSQL point-in-time recovery, or PITR, refers to the recovery of a set of data or a particular setting from a time in the past. PostgreSQL has files called WAL files. WAL stands for write-ahead log. The write-ahead log records any transaction on the database to the WAL log files before it writes the changes to the database cluster's data files. PostgreSQL uses continuous archiving, which is where the WAL files are copied to a secondary storage. Point-in-time recovery uses these WAL files to roll back a database cluster to a desirable point if an accident happens. To perform point-in-time recovery in PostgreSQL, start from the restoration of a full backup, then progressively fetch and apply the archived WAL files up to one of the choices shown below. Recovery target name, which is the named restore point to which the recovery will proceed to, or the recovery target LSN, which is the WAL LSN up to which recovery will proceed to. LSN refers to the log sequence number, which is a unique identifier for each transaction in the write-ahead logs, or recovery target time, which is the timestamp up to which the recovery will proceed to. In order to do point-in-time recovery, the following configuration settings will need to be set in the file PostgreSQL.conf. Archive mode will have to be set to on, which is where completed WAL segments are sent to archive storage by setting the archive command. The archive command is a shell command to execute to archive a completed WAL file segment. WAL level equal replica, which is the default, or WAL level equal logical. Log statement equal to mod, which logs DDL and DML statements such as insert, update, and delete. Note that these steps will need to be done prior to any issue occurring. PostgreSQL server will then need to be restarted for the above changes to take effect. To update the PostgreSQL.conf file, we will use Notepad++. First, we will go to the data directory where PostgreSQL has been installed and open up PostgreSQL.conf. Then we will set archive mode equal to on. Next, we will set the archive command. Here we will use a local folder named Postgres Archive. However, this would normally be set to a folder location on a server. Now we will set the log statement equal to MOD. Next, we can see that the WAL level is already set to the default of replica, so no changes are necessary. Now we will save the file. In order for these changes to take effect, we will need to restart the Postgres service. To do this, we will open a command prompt window and run it as an administrator. Next, we will stop the Postgres service, followed by starting the Postgres service. The following are the steps for performing a point-in-time recovery. First, find the time, log sequence number, or the restore point name to restore your data to. Then take a base backup using PG base backup. Stop the PostgreSQL server. remove the contents of the Postgres data folder, then restore the base backup files to the Postgres data folder, and remove all files from the pg_while folder. They are considered old since we have archiving enabled. Now we add the following commands to the PostgreSQL.conf file located in the PostgreSQL data folder. Note that for PostgreSQL versions 11 or earlier, these commands will need to be added to the recovery.conf file. Next, specify the command where to retrieve archived WAL files from using the restore_ command. Note that this will be the same path that was defined earlier in archive command of the PostgreSQL.conf file. Next, set the action to perform upon reaching the recovery target using the recovery target action. The choices are pause, which is the default, or promote, where the recovery process will finish and the server will start to accept connections, or shut down, where the recovery will stop the server after reaching the recovery target. Then set the target for recovery, which can be recovery target time that specifies the timestamp up to which recovery will proceed, or recovery target name, which specifies the named restore point to which recovery will proceed. The recovery target name can be created using the function pgCreateRestorePoint, or recovery target LSN, which specifies the log sequence number of the write-ahead log location to which recovery will proceed. Next, create an empty file named recovery.signal in the PostgreSQL data folder, followed by restarting the PostgreSQL server. In this example of point-in-time recovery, we will use a PowerShell window. Note that you will need to run the PowerShell window as an administrator. Then we will go to the bin directory where PostgreSQL has been installed. Next, we will launch psql, which is the Postgres Interactive Terminal. Then we will create a database named Random Data. Then we will connect to the Random Data database. Next, we will create a table named SumData, followed by inserting data into the SumData table. Using a select statement, we can see the data that was just added. Now we will exit from psql. Using Notepad++, we will go to the PostgreSQL log folder and open the most recent log file. Next, we will capture the timestamp of when the insert into for SumData occurred. Then paste the timestamp into a new window. Now we will perform a base backup. Then we will open psql and connect to the Random Data database. Then we will drop the SumData table to simulate a mistaken deletion. Next, we will use select pgswitch_wal function to force the segment switch manually to ensure that a just finished transaction is archived as soon as possible. Then exit from psql. Next, we will stop the PostgreSQL service. Then remove all of the items in the PostgreSQL data folder. Then extract the base backup into our PostgreSQL data folder, followed by removing all of the contents in the pg_wal folder. Now we will append the restore command to the PostgreSQL.conf file. Then add the recovery target time and copy and paste the timestamp that we had retrieved earlier from the log file. Note that we incremented the timestamp by 1 second, so the point-in-time recovery runs just after the insert into. Next, set the recovery target action equal to promote. Then save the file. Now we will create the recovery.signal file in the PostgreSQL data folder. Then start the PostgreSQL service. Then using psql, we can see that the table Some Data has been restored. And finally, we will remove the commands that we appended to the PostgreSQL.conf file. I hope you found Introduction to PostgreSQL and pgAdmin helpful. If you have, click on the like button. And to receive any updates to this channel, click on the subscribe button. Thank you so much for watching.